Thank you very much. Thank you for the invitation. I'm happy to be here. So I will talk about probability and a bit of combinatorics today, and about persistence probabilities. So the key word of my talk is really persistence, and I wanted to take a first example where you will understand what it is. So if you go to Paris at Opéra Bastille, you could listen this time to this opera, so Das Rheingold. And if you look at the introduction, so I think it lasts 7 or 8 minutes, just about one single note. And so this the meaning is that there is a nature which is like a persistent state, and at some point something happens, and this is the start of maybe 20 hours of opera. So I recommend. But this is how I will understand persistence today. So it will be a kind of system which will stay in a state, and we're going to understand how it will move from this initial state. So I will report about 2 or 3 joint works. The first one is about with Frank Arzada from Darmstadt in Germany. Second one is related to the talk of Thomas Simon 2 days ago. Maybe you were there. And the last one is some ongoing work also with Frank Arzada. So let me explain a bit what I mean by persistence in probability. So it's a bit related to the previous talk, this Christoffel words. So if you look at the picture, this is this ballot problem. So there is an election with 2 candidates, A and B. And so there is this election, which I can represent with a path in the quarter plane. And every time A has a vote, we move right, and if B has a vote, we move up. Okay, so a very simple random walk in dimension 2. So what is important for the vote somehow is the end of the count. I mean, does A or B win after the election? But here, if you look at the picture, we are interested in all the counts, and I'm looking at some persistence event because I have represented a red path here, which means that all along the count, A, in fact, had more votes than B. Okay, so it's not only that, in fact, they have the same number of votes at the end, but A was ahead all the time. So it's an example of a persistence event in probability because we stay in a domain of my space here. So a second example is about random walks in dimension 1. I mean, even though the first model is also about dimension 1. If you take a very general random walks, you can ask about is it likely or not that the walk will stay in some domain, for example, positive half line or not. So it's a classical question. And if you look at, for example, unbounded random walks, you can end up with very difficult questions about survival of first passage times of such random walks.
But if we have such a red path, does it have some indication that voting is corrupted? So the last moment.
Yeah, exactly. Yeah. So I will not speak about politics today, but and I personally were interested in the random processes in cones. I mean, a higher dimension case, and again, a lot of question about what is the probability to stay in a given cone, and yeah. Okay, so what we have in short is that we have an object which has a size or a time, so n, and we want to describe how p of n, so the probability, will decay with n when n goes to infinity. So it can be exponentially fast or polynomially fast. We want to understand at least asymptotically what is going on. And in my talk today, I will show a few examples where it's possible not only to have asymptotics, but also exact explicit expression. So it's really the main message to go further from just asymptotics. And so due to the topic of the workshop, I also wanted to mention a few physics motivation to look at persistence. And I was able to find a few concrete examples from physics where persistence naturally pops up. And the first one is about this picture here. So this is a kind of surface, and we have droplets of water which accumulate on this surface. And the question is to fix a part of the surface and to compute the time or the probability that it will be dry between time 0 and n. And apparently there is some critical exponent appearing if you look at long time behavior, which is one concrete example where you can have a persistence. And I also mentioned very famous models like Ising model or disordered polymer. So many physical systems can be studied at least partially with this idea of persistence. And the last example is about plate tectonics and earthquakes. In fact, if you are able to understand the persistence of some integrated Brownian motion or random walks, you can transfer this into some concrete estimates about the propagation distance of the earthquake. So it also has kind of a concrete application. Okay, so this is the end of the, let's say, general introduction. And I think Thomas Simon already mentioned these results, but I wanted to speak about it again. So let's look at very general one-dimensional random walks, which for me will be just a sum of n IID random variables, so dimension 1. And so we have 1,000 of ways to define a persistence event. And for me, I will take this quite simple one, which is a probability that the walk will stay non-negative between time 1 and time n. So a priori, it's unlikely. And the question is, how unlikely is it? And if you are a probabilist, you like to define a passage time, so tau. So tau is the first time the walk will be strictly negative. And it's equivalent to reformulate with this tau bigger than n. So exactly the same. And so we have this very nice universality result in probability, which says that if you take xi to be symmetric, so x and minus x have the same distribution, and you also take a density, so no atom in the distribution, you have a universal formula. So this quantity here doesn't depend on the distribution and is given by this very nice central binomial coefficient. And so maybe you know, of course, that if you make the sum of these coefficients, you will end up with this 1 divided by square root x. Anyway, and so if you're interested just in the persistence exponent, you get a square root of n here.
This is Feller book.
Yeah. Exactly. It's a very famous result. So Sparre Andersen, I think, proved it maybe in the 60s or something like this. I know you like Chebyshev polynomials. And so I think Thomas mentioned this proof. There are many proofs of that result. And one of the proof comes from some identity between two generating functions. So on the left, you have the main generating function, for the quantities of interest. And on the right, you have another one which is much simpler because we just have one single variable here. So here we have all the path of the trajectory, of the walk, and here we have just what happens at time n. And of course, we have the price to pay that you have an exponential. And the point is that if you take a symmetric distribution, you will get this 1/2 here. And then you can simplify using logarithm and go back to this formula here. Okay? But in fact, I will not speak about random walks today. I just wanted to mention this result because I think it's so important. And I will move to moving average processes. So this is the main model in my talk. Okay. So what is it? In fact, this is a very simple process. So it's a bit like random walks. We start with xi, which is IID, a sequence of one-dimensional random variables. And we have some coupling parameter theta. So theta is one parameter. And we take just a sum of two variables. So it's called the moving average because in a way, this sum can be interpreted as a mean average. And we just take two such random variables, and it moves all along the time. So why do we care about such random sequences? It's very specific. So in fact, it's nice because it's a kind of one-parameter generalization of IID sequences. If you put theta to be 0, you get just a classical sequence of IID random variables. So it's a generalization of IID sequences. And
this is what Simon wrote in the first line.
Okay. I wasn't here, but
sorry.
No, I'm not sure. I think Thomas maybe wrote a recurrence relation, like he had some process Zn, and I think Zn plus 1 was equal maybe to theta Zn plus xn plus 1. But it's very different because, so the point is that here for me this is Zn, it's not xn. So for Thomas it was kind of random walks modified with some parameter theta, and for me it's really just two random variables, so you know it's different. Okay, so it has a very simple correlation structure because if you take, for example, Zn and Zn plus 2, I mean, it's fully independent. So you cannot imagine a much simpler sequence of random variables. And also it's stationary. So the law doesn't depend on n, for sure. And also if you look at statistics, it appears in many studies because it's used in time series analysis. And there is indeed a family which groups what Thomas was speaking about, and also this sequence, which is these ARMA sequences. Okay, so in this context, so now we have these moving average sequences. We can define the persistence probability exactly in the same way. So the question is to compute the probability to stay non-negative up to time n. And for exactly the same reasons, we can reformulate using a first passage time to the negative axis. So a priori, this is a function of n and theta, and we want to describe this function of two variables. What is nice is that at theta equal 1, we have a universality result, which is quite simple, because at that point, you can prove that you want to compute the probability that all variables are ordered. And of course, by immediate symmetry arguments, you get 1 divided by n factorial. So in a way, we can view this question as trying to generalize this universality with one more parameter and understand how it will go down to 1 divided by n factorial. Okay, so if you draw a path, you will get this kind of stationary law. So it's very likely that it will decay exponentially.
The last universality holds for as atomic?
No, you're right. Yeah, good point. No, indeed, we need to have like a density or no atom. Yeah, for sure.
And the definition of innovation?
So what I call innovation somehow, I mean, this is just the sequence that we add here. So it will be my sequence x of I.
Okay.
Yeah. Thank you. Because this is some other, or maybe in fact it's more natural to define this xn. So this is a new part which enters into the process. So this is the innovation of the process. Okay, so before studying this, we got some inspiration from earlier work. And in particular, there is a nice paper by Orsada, Mukherjee, and Zaitouni, which says that even if we cannot compute the probability in closed form, we can say something asymptotically when n goes to infinity. And this is true for a very large class of Markov chains, and in particular for moving average processes. And the point is that they prove that there is an existence of this lambda here, which is between 0 and 1, and which describes how my probability goes to 0. So we don't know exactly how. We know lambda is a root, a kind of principal eigenvalue for an operator, but we don't know how to compute this value. And in a nice paper by two physicists, Dar and Majumdar, they looked at a very special case when they take uniform innovation. So it means that the xi here will have this uniform distribution over some symmetric interval -1, 1. And in this case, so I will speak about the results a bit later, they were able not only to have asymptotics but also explicit expressions for the persistent probabilities. And this is how we came up with our question. So now we have two parameters. We will look at asymmetric distribution over uniform interval. So we look at this -a1 and also uniform. So this reduces to this question when a is equal to 1. But a priori now we have two parameters. And so what are the questions? Is it possible to get explicit expressions for persistence probabilities? Maybe asymptotics when n goes to infinity. And also because we are going to have two variables, we can make a kind of phase diagram and study the phase transitions between the two different, between all the different regimes. So this is a program of the rest of the talk somehow. So I need to introduce a classical function and a special function theory, which is a deformed exponential function. So we just add this parameter here. What is important is to have this n square as a power as an exponent of r here. And it turns out that this function is quite classical, in fact, in physics and also mathematics, let's say. It's related to some enumerator of label trees, so I will speak about this a bit later. Also about the third polynomial of graphs, and there are some statistical models like a lattice gas where it also naturally appears. And more recently, people were interested in studying the zeros of this function, I mean in the negative half-line. And for example, are there simple, there are a lot of complicated questions on the zeros, or the series expansion of the zeros of this function. So it's really some intriguing function. And so first question, so why is this function important? So I wanted to make a small computation to indeed show you that it will appear naturally. So I changed a bit the persistence here. In fact, I reversed the inequalities, but I wanted to show you that if I do so, I'm going to make the function exponential appear. So it's very simple. Imagine I just want to compute this probability here. So simple computation, I have a successive integration. So for example, xn will be between 0, so this is my condition, and theta x minus 1, and so on. So xi n minus 1 will be between 0 and theta x minus 2. And you keep integrating, and at the end you have dx1 between 0 and 1. And you can see indeed that just if you compute, I mean, from the inner integral to the outer one, that so in the first step we are going to have a theta x n minus 1, and so on. So we are going to have a cumulative powers of this theta here, and because we have a sum of integers, we are going to have this n minus 1 over 2 which appears. Okay, so just to show you that this function really is natural for the model, even if I modified a bit the persistence probabilities. Okay. And so what I'm going to present now is the results of this paper. So I have two variables, a, which is the length of my interval, and n, which is just the number of random variables involved. And I want to have a formula for this persistence probability. And the point is that I'm going to have a number of regions in this parameter space, so in a and in theta, and in each region we will have a different formula. So the first one, and then I'm going to show you the phase diagram. This is a series of the persistence probabilities here. And on the right, so this is the main formula, we have an expression in terms of the deformed exponential function. So everything reduces somehow to this a nice exponential function here. Okay? Evaluated at some function of z, a, and theta. So I will comment a bit more about this formula, but before I wanted to show you this diagram. So the formula which I have shown corresponds to this blue central region here. So we have a bigger region, and a key point, so I will speak about this later, is that we will prove some dualities between the parameters, and using these dualities we can continue the formula. I mean, the formula will be a bit modified, but we can extend the domain to some other domains, for example, the light blue domain here.
So you said the parameters. There is theta as a parameter, the other ones are?
Yeah, so the first one is theta, this is A, which is the length of my uniform distribution. Yeah, sorry. So maybe I should mention it. So we look at this minus A 1. So if you look at A equal 1, okay, so the horizontal line, then we get the Dar and Majumdar result. But in fact, we go much further because now we have a two-dimensional phase diagram. So I will try to explain everything. I mean, how to prove a formula in a given region, how to prove these dualities, and so how to prove this diagram. So, okay, it's a lot of formulas, but maybe it shows again that everything which appears can be reduced to this exponential deformed function which appears a bit everywhere here. And so you don't have, of course, to learn the formula. Maybe, so I will speak about another regime here. There is a big difference between all regimes and the orange one, where you have a rational function, in fact, which will appear. So there is a kind of a drastic change of behavior here in this region. Okay, so again, in each colored region we have different formulas, and now we are going to understand how they interact, or how we can deduce some of them from the blue region. So this is the dualities. So I guess it's important. So we have simple dualities and more complicated ones. So the simple ones say that in fact you can transform the parameter theta in 1 over theta. So I mean it's clear from the model that it should play a role. And you will not modify that much the person's probabilities. So maybe this is a very simple statement. If theta is negative, you can just reverse theta in 1 over theta, symmetry of order 2, and the probability will be invariant. In some cases, it's more complicated. Like if you do so, if theta is positive, you also have to reverse the parameter a. But maybe I can just spend 1 minute to how to prove this quite simple formula. Maybe you are able to do it on your side. So if you write the probability, so a priori this is x2 bigger than theta x1, up to xn bigger than theta xn minus 1. Yeah, so maybe I can start from, let's say, 1 over theta. So I put minus 1 everywhere. And now I just multiply everything by all inequalities by theta. Theta is negative, so I have to reverse the signs. And I get, so x2 now smaller, theta x2 is smaller than x1, and theta xn is smaller than xn minus 1. And because you look at this sequence, which is IID, you can just reverse time, and then of course you will get exactly this Pn of theta. Okay. So a very simple argument. What is maybe a bit more subtle is these two dualities. So now, I mean, it's maybe better to introduce the generating function and to express the dualities at the level of generating functions. And what happens here is that you can also reverse theta in 1 over theta, but now there is this combination of generating functions which appear. And here, if theta is negative, in fact, theta stays the same. Now you have to reverse a. So, I mean, if you want, I can explain a bit this. It's a formal manipulation related to some probabilistic interpretation, of course. And so now maybe we understand a bit more. So here, this is the simple dualities. Here, for example, also here, you can go in this way. And the more complicated dualities I've written here, for example, and also appears here. And so what is the conclusion here? This is that if you want to describe all the phase diagram, you have first to study what happens in the blue region. Then you have all the blue story. Independently, you can compute, for example, the green one. With the easy duality, you get in the light green. And with the more complicated duality, you get the yellow region. And independently, you also have to study this orange thing. But it's how we can split the study in, let's say, key independent parts. And because the blue region is central somehow, I wanted to explain quickly how to obtain the main result.
Kilian, I forgot why you don't have the full plane.
Yeah. Yeah, good question. So the point is that, so for example, trivial reason, if A is negative and so bigger than +1, I mean, you will get something trivial. And the point is that if not, so maybe here, equal to 1, because if you look at this, what you can have is that, I don't know, maybe the variables will be positive because we're on some positive intervals, and the theta is negative. So I mean, for sure, some positive thing will be bigger than a negative. It's just obvious reasons. I mean, you have to think a bit about it, but no complicated thing. Okay, and the proof that we have is in fact direct, at least in the blue region. We start, I mean, a bit as in the board on the right, on the left. You have this integral formula, okay? And we can just perform a kind of successive integrations. And without giving too much details, what happens is that if you do one integration, we are going to move the index here from n into n minus 1, and then we can compute a bit recursively the thing. And we get this kind of nice recurrence relation, which is of not of finite order. I mean, it implies, it involves all the persistence between n equals 0 and n. But still, it remains a kind of a Cauchy type recurrence relation, because we can just take a generating function. It's just a Cauchy product, and it's how we came up with this formula. So it's not always so simple, because what can happen is that if you are in a complicated region, you cannot write such a simple expression. So you have to think a bit about all inequalities, and it will be more complicated. So it's really working well in this particular case, in fact. Okay, so now I wanted just to speak a bit about combinatorics, because there is some interaction between this formula and combinatorial things. And the first one is about a very nice family of polynomials called the Mallows-Riordan polynomials. So we have seen Mallows this morning. So this is the definition. Imagine you take the deformed exponential function here, and you take the logarithm, of that function. Then you, because this series is starting at 1, so this is 1 plus z plus etc. You can make an expansion of the logarithm, and you get a new expansion. There is a trivial part here, some theta minus 1 at some power. And there is some non-trivial part, which is a polynomial, and which we call this Mallows-Riordan polynomials. So it's the first definition of this family of polynomials.
First one is connected graphs.
Yeah. So I will explain what you're right. I mean, there is a lot of combinatorics hidden here. So what I wanted to mention is that if we look at a boundary region, so this is the boundary of the blue region. So for some reason, the persistence is in fact exactly this polynomial. I mean, up to some easy normalization. Yeah. Okay, so now I want to speak more, let's say, combinatorially about these polynomials. So I think we all know about this wonderful encyclopedia where you can find so many sequences. So it's how we came up with it. And indeed, so we can compute a few coefficients of the polynomials and see that everything was already well known. And they have this interpretation as being related to trees and to label trees. So there is this Cayley theorem here, which says that if you count the number of label trees with n vertices, so this is n minus 2. And what we want to do is to refine this enumeration by taking into account inversions. Okay, so it's what I have represented here. So I have a tree, I have this vertex tree here, this root, sorry. And what I call inversion is that if you look at all these trajectories here, you will get inversion if, for example, 5 here is bigger than 4. And so every time you get such an inversion, you count it in the polynomial. And so we have a polynomial g of theta, and theta, the exponents, correspond to the number of inversions in this tree. So it's how we can define combinatorially the polynomial. But of course, I mean, if you see this formula, a priori it's not clear at all how to connect this persistence probability and this combinatorial polynomial. And in fact, to be honest, we have no idea. I mean, the deep combinatorial reasons why it's connected. We have other ways, of course, to understand. If you like recurrences, and it's one of the messages for my talk that we have nice recurrences, we can also characterize these polynomials as the one which satisfies this recurrence relation. So a bit as the persistence before, this is a recurrence really which involves all the polynomials. And if you solve it, you can get a similar, what is called the Gessel type formulas for this generating function. What is nice in this formula is that on the left here, at least if you take theta to be small, you will get a positive radius of convergence. And here, you have a ratio of two series, and each of them has a zero radius of convergence. So it's a nice phenomenon which appears. And so I can continue the story. So there is a connection with the log normal distribution just for probabilists. So this is a famous distribution related to the Gaussian distribution here. And if you compute the cumulant generating function of this, you will end up exactly with this deformed exponential function, and so indirectly with the Mallows-Riordan polynomials. But I mean, for the talk today, I just wanted to mention it, but there is no relation. And maybe something more related is the relation with some volumes of polytope. So this is this one here is called the Cayley polytope. You just take all variables in Rn, and you impose these very simple inequalities, so between x1 and xn. And then you can compute, so it's known for a long time, you can compute the volume of this and prove that this is the value of this polynomial at theta equal 2, exactly. And if you want to generalize this, we can put some theta in the inequalities here. I mean, you replace all the 2 by thetas, and then you get the volume, which is the classical Mallows-Riordan polynomial. I mean, of course, what we are computing here, it's clearly a kind of polytope, so it's not so surprising. Okay, so this answers the question of explicit computation, and now we can move into the question about asymptotics. And so using flageolet and well-known techniques, so Cyril spoke about this morning, we can study the zeros of this function here, and it will give how my probability decays to 0. And so there is a relation between these zeros of the deformed exponential function and so my persistence probabilities. And if you denote z0 or lambda, let's say 1 over lambda, to be the smallest zero of this equation, I mean the denominator here, then we get naturally an asymptotic expansion if you want, or just an equivalent here, using this lambda to the n. So the persistence exponent is related to the first zero of my deformed exponential function. Maybe the prefactor is not so important, but we can also compute it if needed. And so we can understand how it's smooth and how we have, how the persistence exponents decay. Even though, I mean, I have just represented in one region, and I didn't study, for example, the phase transition, the analyticity of the persistence exponents along the border. So this we didn't do. Okay, so before moving to another model, I wanted to conclude with this orange region, which is very particular, and speak about transcendence. So if you look at the deformed exponential function, it's a complicated function in the sense that it is transcendent. So there is no even differentially algebraic equation for this function. And what is surprising is that if you look at this orange region, we have a very simple formula which becomes a rational. And so, if you look at the phase diagram, it's a bit surprising that there is this dramatic change of behavior. So everything is transcendent everywhere, except in this small region. And here, for example, it's even a polynomial. I mean, it's a polynomial, but you have to cut this orange region into an infinite number of subregions, and we have a different formula in each subregion. But still, I mean, it's the complexity is quite different.
You still have your quotient of two diverging series in this rational part?
No, so I mean, then it's quite simple. So we have this formula, and so a priori we have the impression this is an infinite sum, but because of some truncation here, it boils down to some finite sum. So no, it's just a ratio of two polynomials. Sorry. Okay, so just to be a bit clear, so we had, so let's say the first model was about this uniform distribution. And now I would like to speak a bit about another one, which is called Laplace or B exponential distribution. So you will see other formulas involving special functions. So I change a bit the density. So now I look at the same model, so moving average, but I modified the density, which is now this function here. If you take xi equal to 1/2, you have a symmetric exponential distribution. So bivariate exponential distribution. And we wanted to show that, in fact, we can deal with some asymmetry parameter xi. So we still have formulas. But maybe for the talk, you can just think about xi is equal to 1/2. So same probability of persistence, even though maybe there is a small shift because here I involve the n+1 random variables, but okay. Same definition. And also, I don't want to take some time on this. We have similar dualities, again related to the fact of transforming theta to 1/θ, but the arguments are quite similar to this, so it's not what I want to speak about. So we have a priori some similar problem. But now, in fact, we move a bit more into Q calculations. And at the end of my talk, I have a question for you, because there is a question I'm not able to solve, and I would love to hear your opinion about it. So I guess you all know the Q Pochhammer symbol, the Q factorial. If you take a Q go to 1, of course, we get the classical factorial number. And I will use, so there are many different definitions of the Q exponential function. I will use this one, which is one possible deformation of the classical one. And so now we have in mind this universality result at theta equal 1. We know that using this symmetry argument, we have to find 1 divided by n+1 factorial. And what we have is that we have obtained for this Laplace distribution a Q analog in a way of this, which takes this form. So we have isolated this 1 divided by theta so theta is Q, theta factorial. And here we have a function of xi, and very easy exercise. If xi goes to 1/2, you will get 1 here. Okay, so it's a kind of a two variable extension of this universality result. So it's no more universal, but we know how it escapes, let's say, from universality. And if you prefer looking at generating function, you can look at the second formula here, which involves this Q exponential function. So when theta or Q goes to 1, then we can simplify everything, and using the addition formula for the exponential function, you get the classical exponential 1. But of course, in Q calculus, we don't have this addition formula, so we cannot use this, and this is a general formula. So this is an easy case, theta positive. And now I move to maybe the most interesting case. And before, I need to take some notation and to speak about this Euler zigzag numbers. So in fact, the classical definition is this one. We take this explicit simple generating function, and we expand it in the power of z, and then you get this Euler number. I guess you all know about them. So for later in my talk, I need this trigonometric identity that I can reformulate this into this ratio here exercise. But for now, we're just happy with this first formula. And maybe you know that these numbers are related to alternating permutations. And this is the start of the sequence here. And I don't know if I do it correctly, but I think Stanley, or maybe, introduce this Q analog of zigzag numbers, and you do exactly the same, replacing cos by so Q cosine and Q sine. And now it's related again to alternating permutations, and a bit like in Mallows-Riordan setting, what you have is that you can interpret Q as inversions, so not surprisingly. Oh, anyway, so just a notation. And now, so we have two results. First, it will be about the persistent probabilities, and second, it will be about the generating function. So if you look at the probabilities in the case theta negative, so very important, theta is negative, then we have this result that in fact Pn is related So modulo a sum of a weighted sum of product is related to Euler numbers. I mean, this Q analog of Euler numbers. So it's the first formula. And maybe it's a bit more beautiful at the level of generating function. So this is the formula when you take theta equal 1 here. And so we get the classical Euler numbers. And this is the formula if you have a general parameter theta. Again, so theta is negative, so this is why we have minus theta and not theta. And you see, I mean, it's really the same formula as above, except we have replaced 1 divided by 2 here by this. And of course, we have to replace the classical sine and cosine by theta, sine and cosine. So it's a natural Q analog of the classical case. And so final question. As in the first section about uniform distribution, if you want to understand the percent exponent, you have to understand the zeros of the series, so for sure. And if you look at the universal case, what do we do? So we look at the formula here, and we have to solve, so easy, cosine equals sine. So I guess we know how to do it. And we end up with this pi over 4 function, and because we have a z over 2, what we get is that Pn, so decays to 0, and we know how fast, so it will go to 0, like 2 divided by pi. And if you want to do the same now for the Q analog, I would need to solve this equation, which should be an analog of pi over 4. And this, I was not able to find it in the literature. So I mean, if you know how to do it, I will be very happy, because if we know how to, a kind of expression for this, it will exactly give how these numbers, I mean the persistence probabilities, will go to 0. So what is sure is that for theta equal -1, we have to find pi over 4. And when theta is equal to 0, so remember beginning of my talk, we have to find the classical independence setting. So it has to be 2. So we need a function which interpolates between 2 and pi over 4. And of course, which has the property that this should be equal to 0. So yeah, end of my talk. Thank you very much.
Thank you very much. Place for comments and questions.
So for your last question, it could be very nice, in fact, that it could be related, I don't know, to what we discussed with Philippe just 1 hour ago. So that there is a few analogs of many stuff which were introduced by Orchenko and Morlier-Genoux. And they have a way to apply this to real numbers. And it will be very nice if their notion of Q analog will be exactly the one which works on this equation. I don't know, because I am not sure of your Q analog of cos and sine. It could be one possibility. Then it will be.
I mean, the thing that in the literature you have thousands of analog of pi. The thing is to find the good one. But yeah, no, you're right. Yeah, I don't know.
All right. So thank you for that nice talk, and that what you introduced, that Q analog. This is the Bergman representation of Q oscillator, and that was done by Gutta and Massen, and only for Q from 0 to 1, for negative. So probably there should be some probabilistic aspect. We consider the problem from probabilistic, but so my question is, if you also found for negative, or is that Q equal theta? So negative theta you also consider problem or not? Because there is some delicate situation, because this is connected with so-called Q Gaussian we introduced with Roland Speicher, and for positive Q, this is theta function of Jacobi. But for Q negative, this is some problem. There is a phase transition, and that is that. So that should be here also.
Yeah, I mean, in a way, we can say something a bit similar. That if you define the function as a function of theta, we have a kind of phase transition at theta equals 0. But the question of how we can connect the two formulas, this I don't know. I mean, we have two different Q analogs, which coincide, but of course, I mean, it's non-smooth, and I don't know. So two different formulas. But yeah, I will take a look.
Yeah. Another remark is that what you consider quotient theta to n over 2 by n factor of theta, n over 2 is the longest element under in length of inversion in permutation group. So this is something very natural statistics. Yeah. But that what you obtain theta 1/theta, this comes from permutation group.
Yeah.
So some geometry or Kelly graph or something like this. I don't know if you also use this or not.
I mean, the point is that
You are coming to analytic function. Analytic function, this is just only one direction. But if you come for Kelly graph of permutation, you are much better. So I recommend you comes to Kelly graph of permutation and look for your problems more general.
Yeah, sure. I mean, this is just two examples, so we have to find a general theory. But
For your talk,
Thank you.
Any other question or remarks?
Just a question. I don't know if it might depends on you know that there are many choices of Q exponent formulas. Your choice is one of so how much it depends on it?
So it's a good question, but the point is that we didn't choose it. I mean, somehow the formula chose us. So, I mean, it's because it appears to be this Q analog and not another one. But you are right. I mean, in a way, in the first part of the talk, I have kind of this Q n minus 1 divided by n factorial. And in the second one, I mean, I put this, and I know that, for example, this one could also be another Q analog. So it's a good question. Maybe we can modify a bit the distribution and add one more parameter.
Everybody knows that, for example, for Q analog of Bessel function, you have 3 different choices at least.
Now disconnected with geometry of permutation. Because this is the longest element. So when you look from identity or maybe from the biggest element. So this is maybe some.
There are relations between them, of course. Sure.
I have an additional remark. Some time ago, with Professor Alan Solomon, we have treated a variation of quantum coherent states, where instead of using traditional exponential function, we are using your function E of R and Z. But I don't remember the details, it was some time ago. But I know that we used at some point functional equation satisfied by this new exponential function. And I'm not sure that I've seen a functional equation, but have you looked at that?
Yeah, it's a good question because indeed, if you think at the second model, for example, we have a Q hypergeometric functions. Yes. And so for this reason, we have to have a recurrence relation of order 1 between Pn and Pn minus 1, for example. Yeah. And this, I mean, we don't have access to this. So I don't know, I mean, if there is maybe like a more efficient way to see the problem and to have this very compact recurrence using hypergeometric function. I don't know. Yeah, good question.
Okay, so if there are no other comments or questions, we thank you.